Hey, Algebra students. In this lesson, we are going to be talking about graphing rational functions, and this is going to be a tough lesson. Students in the past have found this one difficult because this is not the kind of function that you're used to graphing. First of all, what is a rational function? A rational function is a function whose rule can be written as a rational expression. In other words, we're going to write a rational function as a fraction. Notice I have y on one side, and then on the other side, I have a variable in the denominator, and that's really what makes a rational expression. Rational expressions like this are going to have excluded values. These are values of the variable for which the function is undefined. You'll notice that the first part of our lesson practice is going to be finding excluded values. We'll do that in just a little bit. We call these rational functions discontinuous. Now, they're not the only type of discontinuous function, but they're one type of discontinuous function, meaning that they'll have a break or a jump in the graph. The graph doesn't smoothly move across from one side to the other. There's a break or a jump. And actually, our functions are going to have jumps where they go off to negative infinity and then all of a sudden start again at positive infinity and keep going. You'll see what I mean by that in just a minute. And then lastly, our graphs are also going to have something called asymptotes. An asymptote is a boundary line that a graph approaches but never actually touches. Now, over here, I have an example of a graph of a rational function. You'll see that this graph it starts on the left, okay, and then starts going to the right, to the right, to the right. There's this dotted line, this horizontal dotted line here. It looks like it touches it, but actually this graph approaches that line, approaches it, but it never actually touches the value y equals 2. As I continue to the right, notice this graph just suddenly turns and explodes downward and goes downward at a really fast pace. And it gets really close to a vertical line that it approaches and never touches. We call that a vertical asymptote. Then what's going to happen is the next part of the graph, once this graph reaches negative infinity, theoretically, maybe it reaches 3 when it reaches negative infinity. What's going to happen is this graph is going to start again from positive infinity from the top, and it's going to go down and down and down from 3. It's never going to quite touch 3, but it'll come from 3 as an asymptote, turn, and then approach and approach and approach 2. But even if it goes on to really big numbers, it's never actually going to touch y equals 2. This is the graph of a rational expression, and notice a rational function, and notice that there's a horizontal asymptote and a vertical asymptote. Now what I'm going to do is I'm going to write the equation for this rational function, and equations for rational functions take on, like this anyway, take on a specific form, okay? It's going to be y equals a letter. I'm not going to know exactly what the letter is here, and that's okay. So it's going to be y equals, and then I don't know what a is, so I'm just going to write a divided by x minus, and now my vertical asymptote is whatever number this is. Notice it's at x equals 3. Whatever number is in my vertical asymptote equation is being subtracted from x. It's x minus 3 gives me an asymptote at x equals positive 3. All right. And then this is also going to be plus 2. And then whatever this a value is, that's going to affect the curvature. That's going to affect how smooth my graph is, how far away it comes from the point where the vertical and horizontal asymptotes intersect. So that a value is impossible for me to guess what it is, but it is going to affect the shape of my graph a little bit. The things that I can predict is that this graph is going to have a number 3 here because it has a vertical asymptote at 3, and a number 2 here because it has a horizontal asymptote at 2. So here's what I'm saying. You can write out the equation for your horizontal asymptote by writing another equation, okay? So I have my initial equation, my rational function equation. I'm going to write a separate equation that is a line, a horizontal line at C. What do I plug in for C? I plug in whatever number this is in the formula, whatever number this C is. A vertical asymptote at x equals b, what do I plug in for b? Well, as long as my equation has x minus a number in the denominator, whatever this number is that's being subtracted here, that's what I plug in for b here in this equation. If it's x plus b on the bottom, I have to take that b and make it negative and say that x equals negative b, because the natural state of the denominator of this function for a rational expression is for the bottom to be x minus b. And if it's x minus b, I just take whatever that b is, not negative b. I just take the b and plug it in here. If it's x plus b, then I have to plug the opposite of b in here. All right, now let's take a look at what I'm looking at as we work some actual problems. A, B, and C are really easy ones, okay? Because all I have to do for A, B, and C is find the excluded values. And we've done this before. We've done this before. So for this, I'm going to write out what's in the denominator, x minus 3 equals 0. I'm sorry, I'm going to go over here to this one. We're doing letter A. So I was looking up here. It's 6m equals 0. I'm going to divide both sides of this by 6. I get m, because 6m divided by 6 is just m, equals 0. I'm going to have 0 as an excluded value. 0 is going to be one of the values that that I can't put in to this equation. So on the x-axis, there's a value that if I plugged it in, my equation would be undefined. Hey, let's just go back here. Is there a value on the x-axis if I plugged it into this function? It would be undefined. Up here, the value is 3 because it never touches 3. It has a vertical line at 3, and the graph never actually touches it. The same is going to be true for this equation, except for this equation, it's at 0. All right, let's take a look at letter B here. In this one, I need to take the denominator, m plus 2, set it equal to 0, and we need to figure out what the excluded value is by solving this for m. So in the second one, if I subtract 2 from both sides, m equals negative 2. Negative 2 is an excluded value. Let's just take a look at what would happen if I plug negative 2 in here. If I plug negative 2 on top, there's no problem. It'd be negative 12. But I plug it on the bottom, negative 2 plus negative 2 is 0. Can't divide by 0. There's no such thing. I mean, how many zeros go into negative 12? It doesn't even make sense as a question. All right, and then letter C, I set the denominator equal to 0, and I solve for what m would have to be. So I'm going to add 8 to both sides. 4m equals 8. Divide both sides by 4. M equals 2. M equals 2. That makes this undefined, okay? Now, for all of these, what I'm saying is the expression is undefined if m equals that value. So notice the notation that our book uses for that. They say m cannot equal that value. And what that means is if m equals that value, it's going to be an undefined number. So m can't be 0, can't be negative 2, can't be 2. I just left it as equal signs because I'm just saying those are the excluded values. Okay, so different ways of writing it. It doesn't really matter which one you choose. Let's move on to letter D. In letter D, I'm asked to identify the asymptotes, and I'm going to go ahead and use my equation up here, my general equation, to identify where the asymptotes are. First of all, my horizontal asymptote for letter D is going to be y equals, and then I need to look at the denominator should be in the form x minus b, but it's in the form x plus 1, not minus 1. It's not in its natural form that has a negative. That means that I'm going to use this 1, but I have to make it the opposite. So y equals negative 1 is my horizontal asymptote. And then notice it's plus 0. There is no plus c term, which means it's plus 0. That means that x equals 0 is my vertical asymptote. This graph will never touch x equals 0, the line, or the line y equals negative 1. Let's just check. What happens if I plug in y equals, oh, I got those backwards. Let me just double check here. Because y can equal, oh, so it should be x equals -1 is my vertical asymptote. As I was checking, I realized I had those backwards. So if I try to plug in -1 for x, what happens? If I plug in -1 for x, it's going to give me 0 on the bottom here, and that's impossible. What happens if I plug in 0 for y? Ooh, let's just think about that for a second. Plug in 0 for y. I can't solve that anymore because what happens if I'm okay? So I plug in 0 for y. I'm going to multiply both sides by x plus 1 to get x plus 1 out of the denominator. Well, 0 times x plus 1 is 0. I get the equation 0 equals 4. There's no solution to that. I get nonsense because it's undefined. Okay. So that's how you find your asymptotes. You just use this general equation. Don't worry about all the explanations that I'm given. You just have to use the general equation to do it. Let's do that for letter E as well. For E, my vertical asymptote is going to be x equals -7. Why negative? Because the natural state of the denominator is to be x minus something. This is x plus something. So you need to make it the opposite to make it work. -7 plus 7 equals 0, and I can't divide by 0. Y equals whatever number is being added out here, regardless of positive or negative. So in this case, it's y equals +6 is my horizontal asymptote. All right, let's move along. What about letter F? Letter F, I need to identify the asymptotes and graph each function. I'll show you what the graphs of each function look like. To graph the function, by the way, what I would do is just plug in some values that aren't on the asymptote. So I play like x equals -2, -1, 0, and then 1 and 2, as long as those aren't asymptotes. Make sure you plug in values on either side of the asymptote. So as I'm looking at letter F, I realize that I'm going to have asymptotes at x equals -4 and y equals 0 because there's no c term, so y equals 0. Now, I could draw in the asymptotes first and then draw the curved lines on either side of the asymptotes, or I could plug in a bunch of values. I could plug in -6, -5, -3, -2, -1, 0, or something like that. I'm going to get a graph that looks something like this. Okay. Now, the easiest way to graph these is by drawing in the asymptote lines first. This is x equals -4. It's a vertical line. Y equals 0. And then just put curves that never touch the asymptotes. So I have curve from below the x-axis on this side and from above the x-axis on this side. But you could also plug in, if you want points to put on your curve, just plug in some points. If I plug in -6, I get 6 over -6 plus 4. -6 plus 4 is -2. 6 over -2 is -3. So if I plug in, again, that was, what did I plug in? -6, -3. I can plot that doot on the graph, okay? Maybe I plug in -8. -8 plus 4 is, let's see, -8 plus 4 is -4. 6 over -4 is -1 and 1/2, right? -1 and 1/2. So I would graph -6, -1 and 1/2, and I would eventually get a few points on this curve, and then I could easily draw the curve. So feel free to plug in some points, XY coordinates, and then plot those XY coordinates on your graph to actually make the shape of it. Letter G. All right, so for letter G, I have x minus 6 in the denominator. I'm going to have asymptotes at x equals 6 because it's x minus 6, the natural state in the denominator, which is right. So it's just going to be x equals 6 and then y equals -5 because this one, for y equals, I just plug in whatever is here. This is going to be my vertical asymptote here and my horizontal asymptote here. To graph this line, I'm going to draw in those asymptotes, maybe plug in a few points, and I would get something that looks like this. All right, just checking to make sure we got these right. -4 and 0, 6 and -5. I suppose I should do these ones too. -1, 0, -7, 6.